So here's the content. Yeah, so the Mistral 7B is the paper is published in October last year. And then shortly after, they published another paper about Mixtral 8x7B in January this year. So I think they serve the Mistral AI. They serve both the open source models. They also serve closed source models. So if you look at their website under the research models, so these are all the kind of like open source models under the Apache 2.0 license. For example, this cold store model, Mistral model, I think they are all variants of the Mistral 7B, and then this mixture of experts model. So the overview of Mistral 7B, I think that all the optimization of Mistral models is in how can we develop efficient large language model that has comparable performance, but at the same time we can minimize the kind of the latency and trying to improve the efficiencies of these LLMs. When I look at the paper, I actually do not feel like it's a big change from the Llama architecture. I think there may be many two. Like one is group query attention. But I think the Llama, like the bigger version of the Llama model, they also use group query attention. So if you look at the kind of the description architecture of the Llama 2 model, like for example, for the 34 billion and 70 billion, they also use the group query attention to optimize the latency speed. While for the Mistral 7B, they use the group query attention right away. And then they also introduce a sliding window attention. So many of these two attention mechanism, which I will introduce in the next slides. In their paper, they mentioned that these attention mechanisms collectively contribute to the performance and efficiency of the Mistral 7B. But I think the training data may also play a very important role. But in the paper, they haven't described about what are exactly the training data sets they use, how they curate it, how they clean it up. They haven't described too much about the training data sets. So I would put a doubt here to see if really the performance gain is due to this like more efficient attention mechanism, or is it due to the better training data sets they curate for pre-training the Mistral model. I will describe next about this two attention mechanisms. Like one is the group query attention, the other is the sliding window attention. So the group query attention is the way basically we can, instead of save the value and key pairs for each of the token, you basically group the nearby them together so that, for example, the nearby two tokens, they all use the same copies of the value and keys so that it can greatly reduce the memory used and also speed up the matrix calculations especially at the inference time. So if you are not familiar with the attention, I think the attention is if you simply think of it, it's just like queries and keys, kind of like an inner product to calculate the similarities among the tokens, and then you do a weighted sum of the values, and in the end you get your contextual representation of the token. So that's the attention calculation. And the group query, basically they instead of saving a quick value and key per token, they group the nearby tokens together and they all use the same copy of values and keys. And this copy can be just do a simple mean pool of these values, right? You just calculate the average of these two values, and that give you the grouped values for these two tokens. And there's also this like a multi-query. Basically, I think you can think of it just like as a larger group. Like you just average them all together into one copy of values and keys. And group query is just a trade-off between the multi-hat and multi-query. The second attention is a sliding window attention. I think it's also very intuitive from the visuals. Like originally, the attention will attend all the past tokens in your context, right? For example, the cat sat on the on the chair, right? And then, for example, the cat will attend to the set will also attend to all the previous tokens, basically the and cat. So so this is like the regional attention of the will attends to all the kind of the causal mass, apply the causal mass to all the past tokens. While the sliding window attention, it will limits the how many previous tokens you will attend to. So for example, here you set a window of say 3, right? So you will just attend to these 3 tokens for that word. You may find, well, it will limit the attention that each token will attend to if you kind of limit it by a window function. But the paper also says that actually if you add the layers up, right? For example, even though this layer, it can only attend for these 4 tokens here, but if you add more layers, you actually have a much larger kind of like a context length of tokens that you attend to, right? So because all the upper layer is kind of a summarization of the following of the layers below, right? For example, for this token, if you have 2 layers, it actually attend to all 8 tokens, well, 7 tokens, like by cascading the tokens up. Yeah. So they think that the sliding window attention will improve the training and inference efficiency, and also at the same time it won't hurt the performance much because the effective content next is kind of equivalent to the old way of doing the attentions. Yeah. And if you are doing the sliding window attention, it also makes changes to the buffer cache for the key value pairs. This is a very common trait in the transformer to speed up the transformers. Basically, you save a copy of all the previous key value pairs for the previous tokens, so that the inference is very efficient. I will also have an illustration in the following slides. But for this sliding window, it means that the cache is also limited, right? So instead of you have like a very long cache almost equivalent to the context length, you right now only have a cache for say a window size of say 512. So basically you limit the size of your cache, and it's kind of like a rolling window because you only care about the last 4, right? For example, let's look at this example over here. Like on the next token you're trying to predict, it only cares about the key value pairs of the last 4 tokens. So basically you just overwrite the old ones, right? So for example, it only cares about these 4 tokens, and then the cat, this one, which is outside the window, got overwritten by the recent token. There. Yeah, so basically this is one benefit of sliding window attention, that it will make the cache also smaller, so that you can probably train a better or larger LM with this trick. Yeah.
Question. So is this just to reserve buffer and memory footprint? Is this only for reducing your footprint, basically, these techniques, or are there any benefits to it?
You mean the sliding window or the cache?
Yeah, so if I understood correctly, the cache is a consequence of the sliding window, right? Or is it a separate technique altogether?
It's a separate technique, but it can be combined together.
Okay,
so even without sliding window, you can also apply cache. Like a cache is like saving the key value pairs. So this is a benefit of using cache. You reduce the memory print in your system.
So it's only for memory print. Got it.
Yeah. So that if you do not save, for example, the key value, the keys and values, right? So for example, the purple ones are stored in the cache. The purple ones are stored in the cache. So if you don't store this, you end up recalculating over and over again, right? When you do the do it sequentially. And if you will cache the key value pairs, you can just focus on the attention, kind of the final representation for the new token, for the next new token. So this is just a trick for all transformer or attention-based models. So this is a full architecture of Mistral 7B, and this is the major parameters in the model architecture. So for example, the first one dimension is the size of the embedding. So basically the embeddings are the token embedding, right? Say if it's a word, then it's each word is represented by 4096 dimension vector. And number of layers is like a number of transformer blocks or decoder blocks, attention and MLP blocks in the network. So there's like 32. And then the head dimension is the dimensionality of each attention. It's usually just you can calculate the head dimension by dividing the dimension of the embeddings by number of heads, right? So if you divide this 4096 divided by number of heads, 32, you get your head dimensions. And then this hidden dimension is the size of the hidden layers in the feed-forward neural network of the decoder, right? If you think of decoder, you have attention, self-attention mechanism, mask, self-attention, and then you have MLP on top. So that's your decoder block, and this one is the number of neurons basically actual like a hidden layer in the MLP. And this is like number of heads, number of attention heads. More specifically, because it uses the group query attention, so you also need to set the groups, how many groups, like how many groups of key value pairs, right? So if you set it at 8, and if you have 32 heads, it means that 4, basically if you divide 32 by 8, you get 4, means that 4 nearby tokens will share the same copies of key value pairs, and you do a mean pool of 4 values there. And this window size is for the sliding window attention that you will attend to 4096 tokens, the past tokens there. Basically, it just reduces the attention by half. It actually doesn't reduce that by that much because the context length for the Mistral 7B model is like 8,000, and the window size is 4,000. So it's kind of just cut the attention window by half. And this is the context length of the model, like the longest length of the text it can be processed by this model. And finally, is the vocabulary size, which is how many number of different tokens that this model can recognize. And speaking of the performance versus the Naman model, and I think at the time of publication of this Mistral 7B, they compared it with the Nama 2, 7B, 13B, and also a larger version of Nama 1, 34B. And they claim that the Mistral 7B can have a better performance compared to Nama 2, 17, 13B models in terms of the language understanding, knowledge distillation, reasonings, and comprehension tasks. They also evaluate the math. There's also some AGI kind of benchmark over there, and also specifically code. They see a large improvement in the coding capabilities over there. So, and again, I put my doubt here because I don't think just those two attention mechanisms differences, they may help improve the inference efficiency by a lot, but I do not think that it will improve the coding performance by this much, just by using those the attention mechanisms in their architecture. I more prefer to think that they have a better coding pre-training data sets, better curated pre-training data sets and a better training strategies they use to train this model. But I do admit that the Mistral 7B is maybe a more efficient model in terms of the inference, right? But the performance gain, I doubt whether it is because of that minor differences in architecture. Moving on next, they also have a variety of benchmarks. I think these are all very common, like a different language understanding benchmarks, Q&As, benchmarks, and also this one is for the entry-level Python programming benchmarks and also the math benchmarks. And they compare it, like this is a pre-trained version, and they also even compare it with the Llama 7B. I think this is still Llama 2. So it's like a Llama 7B fine-tuned, specifically fine-tuned version for coding. And yet the pre-trained version kind of, and yet the pre-trained version still has like a slightly worse because the pre-trained is not specifically fine-tuned, have a smaller gap with the coding, but it's able to, but not losing all the other performance across other benchmarks over here in terms of the language understanding and math. Let's move on to the mixture of experts. So the mixture of experts, like intuitively, the framework is like this, right? So we have like several separate experts may specialize in different things, subjects, and then there will be a router network to pick, say, the top 1 or top 2 experts, and then the output is a weighted sum of the top 2. So basically they want to weld this kind of structure directly into the architecture of the decoder model itself. So it's not like it train 8 models separately and kind of combine them together. It's kind of like a big example. It's not like that. It's more of how can we directly weld this information into the decoder block of the GPT model there. And actually, mixture of experts is not proposed by the Mistral AI company. It's actually proposed by Google. So you already recognize some big names here, like Hinton and Jeff, right? So this paper is originally proposed to define this module block in any neural network, right? So they actually originally proposed this to work together with the recurrent neural network in the year of 2017, right? So they add a mixture of experts layers in the LSTM, multi-layer LSTM network for machine translations. So this block, this structure, this neural network blocks is proposed in 2017. And then I think Mistral, like AI company, takes this into the GPT decoder model. And if you look into the mixture of experts layer, so it's kind of just like a one module there, you have your gating network, which trying to select the top 2 experts. The experts is also, you can think of it as a very simple feed-forward network, like just, let's say, one hidden layer. Very simple MLP for each expert. And there will be a gating network. It's also, I think, it's also MLP to select which is the top experts to pick, and then the output is just a weighted sum from this gating network.
Is there anything special about the number 2? Did they try different number of experts and settle with 2?
No, they pick 2. I don't think they have done any ablation study to try out with different experts there. And also in this paper, like this original MOE paper, they also use 2. So it seems like 2 is a magical number, and people don't want to waste additional resources to run different combinations, which may be costly. So they just stick with 2.
Yeah, that's the trade-off of adding maybe more versus quality. I'm curious how it changes, maybe by a tiny bit, and it's not worth it, or
yeah, I think it's a trade-off between the I will talk about next. What is a trade-off? It's a trade-off between this cost performance Pareto frontier. So this frontier describes about the my mouse. This describes about the performance. So the x-axis, are you able to see? Oh, let me. So the x-axis is the performance, right? And then the y-axis is the throughput. Kind of is the cost. Say like per USD, how many tokens you are able to process, right? And there will be a frontier over here, which means that, for example, under this cost, what is the best performing model, right? Over here, and as such. So for example, with a budget of cost, what is the best model that you can use? So basically, there's a cost performance frontier that the model wants to get to the state of the art. So the state of the art, I don't think it's not fair to compare large models to small models, right? Directly. It's better just to put every model on this cost versus performance. And if that model balance the cost and performance well, and if it sits on the frontier, then it is kind of the best model in the portfolio. There. So this, I think they specifically designed the sparse mixture of experts model so that it sits in this cost performance frontier. And also it outperforms Llama 2 7 billion with 5 times faster inference speed, just because they're active, even though it's around like 50 billion parameters, they're active. Active parameters actually is just around 13 billion. So that's why they able to get 5 times faster inference due to they select the top 2 experts because they are not using 8 experts in that module. They just pick top 2 so that they kind of can gain this 5 times faster inference. And also it says it's a drop-in replacement for GPT 3.5, so without sacrificing the performance. And also this model is pre-trained on multilingual data sets so that it has also beats the benchmark across different languages. I also observed that when people trying to create a multilingual model, they also choose to use this Mistral model. It seems that this model also has a better multilingual capabilities there, which is again how they create the pre-training data sets. And this one also allows a context of 32K tokens and this under this open source license for commercial purpose use. And if you look at the parameters of the models, it's almost the same as Mistral 7B, with the differences. One is mainly in the context length. They greatly increase the context length for this. Vocabulary size is the same, and they have some like additional parameters for the number of experts, like say 8 experts, and they pick the top 2 experts at each for each token input token. There are some myths about Mistral 8x7B. So 8 experts, and actually it's not 56 billion. So there are a total of 46.7 billion parameters. I think they give this 8x7 billion just it's kind of resonate better with the audience, easier to remember, rather than put it as 46.7 billion total parameters. And the gating and also the attention modules are shared across all the experts. So basically for all 8 experts, they have exactly the same attention layers and the gating functions. And also this model, Mixtral model, has fewer active parameters comparing to 17 Llama 2, 17 billion. So even though the total parameters is 46.7, but due to that they only pick the top 2 experts out of 8, so the actual active parameters for each input token is only 12.9 billion, so which is smaller than Llama 2. So which means that the inference is comparable to a smaller model, but the performance is beating larger models. So that's the kind of the advantages of using the sparse mixture of experts models. So, and again, actually the mixture model is basically just replace the feed-forward module by this routing network and by these 8 experts in the basically 8 separate feed-forward network as the experts here, and there will be a routing gating functions to pick the top 2, and also they take a soft max of the output of the routing so that the weights sum up to 1. Right, so it take the top 2 and get a weighted average. That's the final output. So for the details, actually this calculation is from the Hinton's and Jeff's paper. The details of calculation is just a weighted sum of all the experts network. And then for the gating function, it's just kind of like a linear weight. You apply a linear weight to the input, and then you pick the top k, and then you apply the softmax so that you got the values, say between 0 and 1, and also they sum up to 1 for the gating outputs. And then the final, basically the final output is this. So this is the routing gating function, and this is your experts model. So actually expert model is a very simple model. It's just like a one hidden layer with a switch glue function, like a general linear unit function. So if you think about like a switch glue function, it's kind of like a ReLU. ReLU is the simplest gated unit function, while the switch is like kind of have more flexibilities in terms of the shape of the curve, but it's the overall trend is similar to ReLU. But it has a parameter to adjust, like how fast and how smooth it want to increase after 0, and also it's differentiable at 0.0 there. Yeah. So the expert actually is a very simple expert in each layer, but because you have 32 decoder blocks stack up together, and that gives you the power of the network to model complicated patterns. All of this is learned. So the switch beta, so this because the switch function is a beta to control the shape of the curves. So beta is learned. This gating, which top two to select is learned. The expert is also learned, right? So the expert is controlled by this matrices like W and V over here. So it's like a gated units of linear transformation there. So all of this is learned. Experts is learned, gating is learned. Yeah, and even the shape of the gate is learned. So this is the performance. They also compare with because this paper is published like the beginning of the year, so it has the full performance for NAMA 2, like a 17B. Like it shows the Mistral 8x7B can beat the performance of NAMA 2 70B. There, especially I think, especially in coding. Yeah, somehow they got like a very golden pre-training data sets for code, I think. And I do think the mixture of expert architecture may also play a larger role here. But at the same time, they also have a very good training data sets for coding, I guess, because it's very consistent to see that the Mistral model has very good performance in the coding capabilities. Yeah, coding and math. It's like, and then for this, I don't know, like BPH and this AGI evaluation, the 70B model still wins over the Mixtral model. But for math and coding, it's better than the 70 billion model. The pre-trained version. So all of these models are pre-trained only, not specifically fine-tuned for any task. So they show the kind of the curve and definitely see that the Mistral model kind of wins over the curve there. So, well, I don't think whether we can put the Mixtral 8x7B here. It's more likely here. So the Mixtral is like a 46 billion. So these dots should be more likely here. But here it still shows that the Mixtral model is more effective. And again, architecture-wise plus data-wise. Yeah.
Is it because during inference you only use 12.9 billion, like 13 billion? Maybe this inference.
Oh, yeah. If you think about the active parameters wise, yes.
I think so, yeah.
Yeah, if you think about like active parameters at inference time, yes, yeah, I think you say it correctly. Then it can be put as 13 billion if you think about at inference time. But if you think about each token have access to how many total number of parameters, then it's around 46 billion. They also show their multilingual benchmark, and it clearly, I think in production, people also find the Mixtral multilingual capabilities is also very good. comparing to others. So I think I do see people like kind of like a fine-tune Mistral models for all the other like a multilingual. If you want to fine-tune, like find a pre-trained model to fine-tune for a multilingual task, this mixture of expert model usually is the top topic for the multilingual capabilities. This leaderboard is also very interesting. So this is a chatbot arena. I think the evaluation is mainly from humans to give some up and down. So they kind of just have like a leaderboard in terms of what is the chat capabilities of all the open sourced and closed sourced models at the time of publication, beginning of this year. So this screenshot is like December 22nd last year. Mixtral is kind of the top one especially the open source one on that leaderboard. And at that time, like GPT-4 model still dominant here, and then comes up with the cloud model like at the end of last year. And we all know like the landscape shift a lot till now. So that's why I copy over today, like what does the leaderboard look like? And because for the new model, because for example, the Llama 3.1, right? It's recently released. It takes a while for it to move up the rank. So it's not because it's not like a immediate ranking of all the models. And I think for Llama 3.1 to catch up here, it takes a while. This one also resonates with the question asked earlier. It's about the consistency of the experts. It selects from token to the next and the next to the next. So this is like a selection portion of how often that this let's say 8 expert, right? So there are 8 experts here. How often does that experts get picked? At layer like the lower layers 0, 15 up to 31 layers, like this is almost the highest layers there. And then the colors indicate, say, if you this is in the archive domain, this is in the GitHub domain, like if you process the tokens like in different domains, they want to see whether there's like specific experts like got picked more often at different layers. So basically what they say is like at earlier layers, it's almost like a random, like the top 1 or top 2 experts got picked is quite random. And then when you move up, you start to see some picks. For example, for the math over here, like the experts 1 and 2 kind of got often picked, like more often picked than the other experts over there. And for example, Wikipedia, the more often ones are experts 2 and experts 7. So like at a higher level, it seems that the expert seems to be specialized in some domain, but yeah, so it's still kind of not that dominant, but it still shows up some specialization in certain domain. Yeah, so this is still the interpretations about first choice or first or second choice. So this is talk about like a consistency of assigning the same, picking the same expert at each layer. So like from this token to the next token and to the next, whether they keep consistency in picking the top first or top second choices to show the consistency there. And again, I think they what they're trying to say that it seems like layer 0, the consistency is also random. Like moving from token to token, there doesn't seem any pattern or consistency. But if you move up at higher layers, you start to see some consistencies over random picking. Yeah. So I think that's why I put the myth there, because I feel it's also a little bit counterintuitive. This is a sparse mixture of experts model. This is just one one sparse mixture of experts architecture for one model. It's not like separate model. It's just one model trained on one big corpus. And it does not specifically design expert separately, but lets the expert at each layer, a very simple expert, at each layer to figure out themselves based on the training data, pre-training data that you feed it, right? And the benefits of the MOEs, and also it's very clear. First, it gives each token access to a large number of parameters, for example, 46 in this model. But at the inference time, the active parameters is small, right? It's still around 13 billion instead of 46 billion. So that can give you the benefits of large models, but at the same time, also the benefits of smaller model so that you can reduce your inference cost. And the expert specialization, as the author claim, is not as straightforward as one may think. The interpretation is still hard. It's not that straightforward. It's not intuitive, right? Till so far, people don't know what exactly is the expert that is learned from the data, from the results. Although ideally, we may want to have like expert in Wikipedia, expert in coding or in math. Maybe that is the future direction, that we want to put some constraint on the experts, or we give more guidance of to understand the world. These are the expertise we want to have, right? And we can guide the kind of provide more prior knowledge to better initialize these experts in the beginning. Maybe that's a good future direction for research and also for interpretability. And also in some the missed question, I still don't have any information at all. Is like what data sets, how they do that to pre-train the model. Because if you really want to justify, oh, your architecture is the best architecture there and it gives you this much performance gain, you'd better pre-train it with the same data sets. For example, for the Llama 2 70 billion, right? Say if we want to compare Llama 2 70 billion with the Mixtral 8x7B, we'd better just pre-train them with the same pre-training data set and see which model gives us the best performance later on. And that is the fair comparison for the architectural differences. But right now, I don't think these two models use exactly the same pre-training data sets. So it's still hard to say whether that performance gain is due to the architectural differences or due to the big performance gain, especially in coding, right? Because for some other benchmarks, we still see Llama 2 70B wins over the mixture model. So it's still hard to tell like whether it is due to the architecture differences or is it due to just the pre-training data set, because the mixture has a better, higher quality data sets, especially in coding, right? So that is still the miss to fix, but I think people right now favor this mixture of expert model is mainly for their inference speed, right? They kind of have the benefits of having a larger model, at least have access to a larger parameters, but at the same time, like the inference is at a smaller scale because you just pick the top 2 out of 8. So I still think this architecture is very clever and very efficient, and there's still lots of research opportunities and directions in terms of, for example, how to set priors for these experts, whether there's a better way to interpret these experts, right? So that we can kind of design, curate better experts or guide the LLM to train better experts. There, I think that all leads to the future direction. Maybe mixture model will do that, or maybe like another open source research community can achieve that. That is the future direction in this in this sparse mixture experts model in LLM.